Yeah. Wenyang, are you here?
Yes.
Yeah, can you start sharing your screen?
Okay. Okay. I see.
Yeah, can you try to go to the full screen mode and
Yeah,
check if everything's working?
Okay, let's see. Right, you can see my pointer, right?
Yes. Okay, it works perfectly. Thank you. Yeah, next talk we'll have Dr. Wenyang Qian from Iowa State University, and he's going to tell us something about lifelong approach to hadron structures with quantum computing. Wenyang, please take it away.
Okay, thank you very much for giving me this opportunity to present our recent work, which is a lifelong approach to hadron structures with quantum computing. Here I show an outline. So in the first part, I'll briefly introduce quantum computing, introduce some background terminologies. The second part, I'll talk about lifelong Hamiltonian approach. And I will show the effective lifelong Hamiltonian we used for the lab mesons, and also we showed our recent result about the meson spectroscopy and calculation of observables. And the third part, I'll focus on the application of quantum computing to the lifelong Hamiltonian approach. I'll talk about problem formulation, Qubit encoding, and unitary ansatz. And particularly, I will focus on the variational quantum eigensolvers that we use to do this computation. So just a refresher introducing the quantum computing. So we have classical computers with lowest bit of information is classical bit, which is 0 or 1. So implementation usually by electric voltage, low or high. So you have classical gates, AND gate, OR gate, and NOT gate, and it has a deterministic nature to it. So basically, you can visualize it as a switch. On the other hand, we have the quantum computer. So the lowest bit of information is the quantum bit or qubit. Basically, the information is a two-level quantum system. And we have quantum gates, which are unitary operators that you act on those states, which is very different from a classical computer. Is that for quantum computers you can have superpositions and your state will collapse when you take measurements. So you can visualize it on the block sphere. So in theory, it can solve problems that a classical computer can never be able to solve. So we have huge development in the past 40 years. So starting from the Toffoli gate in 1980, and then we have the Shor's algorithm, factoring large numbers in 1994. And recently we have the variational quantum eigensolvers, which incite a broad application in quantum chemistry since 2014. And most recently, we also have application using quantum machine learning techniques. So currently we're in a stage of noisy intermediate scale quantum, the NISQ era. So we have devices whose qubits and quantum operations are substantially imperfect. And we're gradually stepping into an era of quantum advantage. So we can have a purpose-specific computation that involve a quantum device and that cannot be performed classically with reasonable time and resources. So major areas of quantum computing application include quantum Fourier transform, and quantum search algorithm, and quantum simulations. So especially in quantum simulations, it's pretty much near-term applications. So in this talk, I'll focus on the VQE application. So why are we interested in using quantum computers? So just like Richard Feynman says, nature isn't classical. So if you want to make a simulation of nature, so you better make it quantum mechanical. And there's a vast amount of encoding information in a many qubit state. So the total state space of n qubit goes with the 2 to the n. So nature does all this calculation for you when you apply the unitary operations. And there's also high scalability in quantum applications, so which I will show in this talk later. And many body problems and quantum computing are similar by nature, and we have seen a rapid progress in quantum hardwares in recent years, with improved scale, quality, and speed. So, and then I will talk about the formalism that we used. It's a lifelong Hamiltonian formalism, and specifically we used the basis lifelong quantization approach, or BLFQ. So it employs lifelong dynamics. So we have so in the lifelong we have a simpler dispersion relation, And it's a Hamiltonian approach. So the eigenvalues will become the mass spectrum, and the eigenfunction will give us to the observables. And lastly, it's a basis function approach. So it allows us to explore symmetry. So this approach has been applied to many Hadron systems, that's a Quirkonian and Boltzmannian, and Hamiltonian, Boltzmannian, heavy light system, and so forth. So in this particular application, we're applying the model to light mesons with valence quark and quark Fock sector. So this will be the form for our Hamiltonian. So in the first two terms are the light from kinetic energy, and the third and fourth term are the confinement. So this one is the holographic transfer of confinement, and this is the longitudinal confinement. And VQ stands for the one Coulomb exchange, and H gamma phi is the pseudoscalar contact interaction that I propose for light meson in particular. And notice here that the MQ and MQ bar are the mass of the quark and n-dot quark. And this kappa and this kappa here are the confining strengths. So these two variables are needed to be fitted with regard to the experiment. And then it's a basic function approach. So the basic function consists of a transverse and longitudinal part, and they are truncated separately. In the transverse direction, we use the 2D harmonic oscillator, as you can see here. And the Mx basically controls the energy scale of the oscillator. And in the longitudinal direction, we have the Lmax, which controls the longitudinal resolution. And they together, they give us the lifelong wave functions. And by diagonalizing the Hamiltonian, we obtain the mass spectroscopy in the light sector. As you can see, the black box are our BFQ result in theory, and the red data with uncertainty bar are the PDG result. And in particular, this spectrum is truncated at this cutoff, Mx equal to 8 and Mx equal to 24. And since it's Hamiltonian approach, conveniently we obtain the lifelong wave functions. So here I'll show you the lowest the lifelong wave function, which is for the pion. So here's the singlet state, and this is the up and down lifelong wave functions. And in addition, it allows us to so lifelong wave function enable direct access to compute the decay constant, charge radius, elastic form factors, parton distribution function, and their evolutions, and so forth. And in particular, I show here the calculation of parton distribution function, a PDF, where we use the decay equation to evolve our initial PDF to experimental scale. So as you can see in this graph. And I will also compute the parton distribution amplitude of PDA. And we use the ERBR evolution equation to obtain the result and compare with the experimental scale. And so the focus of my talk today will be to look at the variational quantum eigensolvers and how to solve the same physical problem using quantum computers. So VQE is directly inspired by the variational principle. It's basically a hybrid approach. So the core idea is to use a parameterized unity ansatz or agitated gas that can produce the trial wave function in order to produce the obtain the lowest eigenvalue via continuous optimization. So here I make this diagram, illustrate the procedure for the workflow of VQE. So the green box are represented on as what you can do on classic computers, and the red box represented what you can do on the quantum computers. So you can see it's a hybrid approach. So in the first part of the preparation of the problem, we define the Hamiltonian for the physical problem, and we will map the Hamiltonian to qubits. So this part you can do beforehand. And in the actual VQE algorithm, in the first step, we will use the unitary ansatz to evolve our initial states. And so this will be done on the quantum circuit using various kind of quantum gates. And then we will measure the Hamiltonian operator on the qubits by looking at the count histogram you obtain from the various quantum backends. And this measurement will then be sent back to the classical computer, which will compute the cost function, such as the Hamiltonian expectation value, which is in the case of VQE. And those values would then be optimized by the optimizers you use on the classic computer to obtain the parameter that you need to be used for the next batch of iteration. So, so this is the traditional workflow for the VQE. And right now we also have a new approach called SSVQE, the subspace search VQE. So the same idea applies. You might have different you have different changes at some certain steps. So as the first speaker talked on Monday, so typically nowadays, when we look at quantum computing application, we have to adapt the problem to a smaller size in order to fit onto the quantum computers. So for our initial application on quantum computers are simulators, which truncate our basis function to the following. So the Mx equal to Lmax equal to 1 will be the smallest non-trivial Hamiltonian that we can have in this model. And also Mx equal to 4 and Mx equal to 1. So this two Hamiltonian have parameters listed as follows. So the first Hamiltonian will be a 4x4 Hamiltonian, and second will be a 16x16 Hamiltonian. And so to solve this problem, we'll use a different encoding. So in this work, we look at the Jordan-Wegener encoding and also the compact encoding. And we also look at different variational ansatz, such as unitary coupled cluster ansatz and hardware-efficient heuristic ansatz. And two different algorithms that I mentioned will be the VQE for finding the ground state, and that's the SSVQE for finding the full spectroscopy. So I will talk about these three in details in the coming slides. And most importantly, with this approach, the lifelong wave function will be directly embedded on the qubits. So additional physical observables such as decay constant can be computed directly on quantum circuits. So just looking at the smallest non-trivial Hamiltonian, so it will be of this form, and the unit, all units are in MEV squared, and the basis function I mentioned earlier. So this is the basis function encoding that we used on the qubits. So when you have a direct encoding, so it's directly encoded on the qubit, and you have compact encoding, you can encode your basis function like this. From second quantization, the Hamiltonian can also be thought about as in terms of creation and annihilation operators. So if we focus on only the single body interactions, and we can identify the Hij as the Hamiltonian matrix element as shown in the matrix here. And in terms of the qubit encoding, so as mentioned, we have looked at the direct encoding. So we use Jordan-Wegener encoding, basically map directly from using the 2x2 polyspin matrices. So basically, we represent the creation annihilation operator as follows on the circuit. And the Hamiltonian you see earlier can be translated into a Hamiltonian with polystrings, which can be represented on the qubit on circuits. And in general, for a n by n Hamiltonian, a capital N by uppercase N by n Hamiltonian, you will need n many qubits to encode it using direct encoding. And then on the other hand, we also look at the compact encoding, which we utilize the orthogonal basis formed by the polystring on the trace. We can further reduce the Hamiltonian. Basically, the reduced Hamiltonian will be as following. We use the trace, which use property of the trace of the extended polystrings to map this Hamiltonian onto the smaller space. So the compact encoded Hamiltonian will be of the following. As you can see, for a n by n Hamiltonian, we will only need log n many qubits. So it's a logarithmic improvement. And in terms of the variational ansatz, so like I mentioned, variational ansatz is an educated guess of the unitary circuit with parameters to be optimized in each iteration. So traditionally, people have used the unitary coupled cluster ansatz, or the UCC ansatz in chemistry. It's motivated by the coupled cluster method. And the idea is to use the excitation operator so that you can evolve your initial state to your expected final state. And the operator, excitation operator, is directly related to the Hamiltonian that you constructed, where this setup is your parameter to be determined. So because of the encoding that I mentioned in the previous slide on the qubit, so eventually the A dagger A's, they will all be represented as polystrings. And for quantum computing, the exponential polystring is easily translated into circuits. So for example, if you have a exponential of a polystring like this, and it will correspond to a circuit like this, where you have the Hadron gates, and you have the rotations, and also you have the control X and the rotation in the middle. And on the other hand, we also look at the hardware efficient ansatz. It's a newly proposed ansatz back in 2014. It's a heuristic ansatz. So it basically consists of alternating layers of single qubit rotations and entangling blocks. So as you can see here on 2 qubit, you have the rotations here, and you have the, so this will be the initial rotations here. And you have the entanglement here using the control X. So this will be a very simple entanglement. And you have the single qubit rotations here. And depending on what you need, you can use various layers of alternating single qubit rotation entanglements, and the form can be different in each layers. So this has been proven to work for many general problems. So speaking of the optimization algorithm, so the variational quantum eigensolver has been a standard algorithm used in chemistry, and it enables us to find a ground state. So you begin with an initial state, and you use your unitary, you pick a unitary ansatz to evolve your initial state to some final state. And then you measure the cost function, which happens to be the expectation value of the Hamiltonian. And then this will be repeated until you reach convergence. And recently we have this subspace search VQE, SSVQE in 2019. So it helps to find the excited states. And one particular version of the SSVQE is called the weighted SSVQE, and enables us to find up to the case excited state. So basically allows us to find a full spectrum. And the workflow of the algorithm is as follows. So you begin with a set of orthogonal states. This is very easily to do on quantum computer because basically all those computational bases are orthogonal. And then you evolve all of them using the same unitary ansatz. And then you have the final state for each of them. And then you compute the expectation value for all of these states. And then the cost function, the cost of the function will be a weighted sum of these expectation values, where the weights is a specific design as the strictly decreasing weight vector, prioritizing low-lying states. So for example, so if I set my cost function like this, where the weights are 1, 0.5, and 0.25, then the state correspond to the weight of 1, which is highest, will become your ground state, and the second weight will become your the state correspond to your second weight will become your first excited state, and so forth. So in this way, via one optimization loop, we obtain the full spectroscopy of all those states. And here I show you the result of, so first I'll show you the result of the VQE for the smallest non-trivial Hamiltonian. So in both figures, the vertical axis corresponds to the mass value of the ground state in units of MeV squared. And the horizontal axis is the number of iterations we have in the VQE loop. And so we have considered SV simulator, which stands for state vector simulator. It's a noise-free exact simulation. We also consider the quadrant simulator. It's a simulator with ability to sample noise from 8,192 shots per measurements. We have also considered IBM-Q Manila, which is a real quantum backend. So it's 5 qubit backend with 32 quantum volume and about 2K Klops, and with some readout error and with the same amount of shots per measurements. And so So on the left, you see the result of VQE with direct encoding, and on the right, you see the result of VQE with compact encoding. So in the direct encoding, the initial state, as I mentioned, will be a 4-qubit initial state. And for the compact encoding, the initial will just be a 2-qubit. So all results agree with the exact ground state energy, I think within 2% error. In particular, as you can see, the real quantum backend result, the IBM-Q Manila result is shown here with red. And for different simulators, we have also used a combination of different optimizers. So we have the traditional Kobila optimizer, and we also have the Newtonian optimizer, BFGS, and we also have the so-called quantum natural stochastic optimizer. So this optimizer is the quantum optimizer on a classical computer. Basically, it can handle sampling noise or any noise you have for a result. There's a fidelity of the measurement attached to the optimizer. And it's important to mention that on the left, we use the unitary couple cluster ansatz. So it has 50 gates. On the right, we consider the hardware efficient ansatz with 9 gates with one layer. So it's very shallow quantum circuit. And here's the result of using SSVQE approach, also looking at the same Hamiltonian. So we will expect to have 4 states in the spectrum for the Hamiltonian. And on the left, I show you the SSVQ result with the state vector simulator. On the right, I show you the SSVQ result with the quantum simulator. Unfortunately, I did not perform the calculation with real quantum backend for SSVQE. But as you can see, with enough iterations, we are able to obtain the agreement with the classical exact results using quantum simulators. And in particular, the cost function that I designed is as follows. So basically, this cost function tells you that the 0,0 qubit will evolve to be the ground state, and 0,1 qubit will evolve to the first excited state. And as you can see on both figure, on the left with the state vector simulator, the 0,0 state represented by blue line will gradually evolve to the ground state, and 0,1 state, initial state, will gradually evolve to the first excited state, regardless of their initial position, because the initial parameters are random, so they could be anywhere. But you can see the spectrum always emerge in accordance with the specific weight order that you set in your cost function. The similar observation can be seen on the right as well. As I mentioned, the state vector simulator is an exact simulation, so you will not expect to see any noise whatsoever. But for the quantum simulator, there's a intrinsic sampling noise attached to it. So we use the 8,192 shots. So in the beginning, there's a lot of noise due to sampling, but in the end, you can see the agreement is quite exact. And different optimizers have been used. And so we also extended this to the larger Hamiltonian that I mentioned. So this Hamiltonian is much bigger than previous, and it's a 16 by 16 Hamiltonian. And so we only look for the lowest lighting spectrum. So actually lowest 4 states instead of all 16 possible states. And as you can see, the cost function is constructed in a similar format. So the 0,0,0 qubit will expected to approach the ground state. And in both cases, we use the compact encoding with hardware efficient ansatz and 6 repetition layers. So there's a lot more parameters, it will be 53 parameters. So it's much bigger circuit. And the agreement with the exact classical result isn't ideal. I should mention that. As you can see, the third excited state is quite some difference between the simulation and the classical result. And especially for the quantum simulator, there's even more noise in the end. So one good thing about this VQE or SSVQE paradigm is that it allows us to compute other observables by using what we obtained from the spectrum. So decay constant is one thing we tried. Decay constant is defined as the vacuum to hadron matrix element of the current operator. So in our particular BFQ basis, the decay constant can be written as the following, which then, if you represent it using basis functions, it's basically linear respect to the basis function. So in the VQE or SSVQE, the lifelong wave functions is basically directly represented on the qubits. So we can compute these observables directly on the circuit as well. So it's proportional to the final state of the circuit after the unitary evolution, and basically dot with the a vector. And this can be constructed as expectation value like this, and we can obtain the operator in the middle, and then we translate the operator on the quantum circuit using direct encoding or compact encoding. So for instance, in the smallest non-trivial Hamiltonian, the operator that you use for the decay constant would be simply like this. And here I show you the result of the decay constant for lowest two states, the pi and rho, from the SSVQE result. And the experimental decay constant are around 130 MeV and 216 MeV respectively. And as you can see, the horizontal, if you compare horizontally, you see the agreement between the simulators and the exact result that you get when you solve the problem classically. And as you increase your basis size, your agreement is still, your performance still agree between the simulator and classical result. And you see the difference between the pi and the rho decay constant. As you expect, if we go to higher basis, this will be better agree with the experiments. So the uncertainty or sampling error in the quantum simulator is the result of measurements from the 8,192 shots. Basically, we calculate the standard error of those shots. And in addition, parton distribution function is also something we can compute on quantum computers. PDF is the probability of finding particle with longitudinal momentum fraction under some factorization scale. So on the basis BFQ basis, this can be represented as the following. We can use the projection operators directly compute the PDF on quantum computers as well. And the PDF operator would depend on X, so that's different from the decay constant. So for example, the qubitized operator for calculating PDF at some particular longitudinal momentum fraction can be written as this. And some instance of this PDF operator is shown here. And here I show you the result of the PDF we obtain. So, for those two low basis truncations, the PDF for the lowest two states are comparable due to lack of longitudinal excitations. But you can see in general they agree with the exact calculation quite well for the case of pi and rho. And for the larger basis, however, so we notice the PDF is not normalized anymore due to the lack of normalization for the lifelong wave function at this cutoff, which is also, as you can see in the SSVQE spectroscopy, the results are not in exact agreement. So another thing that would be of interest would be to compute the hadron matrix element. So that is the key to compute the transition form factor such as and decay width, which allows us to probe internal structure of the bound state. So in this case, a particular physical process would be interesting would be a vector meson to pseudoscalar in this case. And SSVQE offers opportunity to do such computation as well, because you have all those states available to you on the circuits after your optimization. So what you can do is basically you want to calculate this expectation value. But notice the initial and final state are not the same. So you can use this superposition trick of the incoming and outgoing meson states. So you construct your you first compute the observable expectation as the real part and imaginary part. And in each, for example, in the real part, you can break it into several pieces, and you can compute them separately on a quantum circuit. And one such piece is uses the superposition of the initial and final state. So this is a very neat trick. And on the quantum circuit, this is relatively straightforward to realize. So the initial quantum circuit, for example, to calculate the real part are listed here. Basically, you will only need the X and the head mark and the S and the control X gates to compute that. And if you want to compute the imaginary part, you just need to switch the head mark with SHS gates. So here's a summary to our recent work. So we presented two promising quantum computing approaches, the VQE and SSVQE, to find the meson spectrum and observables on light-from for light meson system. So we found that basic light-from quantization approach works well with the VQE and SSVQE approach. Some of the future plans include that we want to optimize the VQE and SSVQE program to solve the original Hamiltonian, hopefully, and compute on real quantum backend. So we already tried that on quantum backend using the newly VQE client program by Qiskit. And so just to give you an idea of how the scaling of the Hamiltonian goes. So our original problem was mx equal to 8 and mx equal to 8. But as you can see, if we just go to mx equal to 8 and mx equal to 1, I think I reversed the order here. So if I just go to mx equal to 8 and mx equal to 1, it will be a 32 by 32 Hamiltonian, which will include 5 qubits. And if you go to a larger longitudinal excitation, it would be 6 qubits. So there's really a logarithmic scaling that you can have for compact encoding to solve this kind of problem. And the other thing that we'll be interested will be the calculation of transition matrix elements of an operator using SSVQE approach. This will be unique since it's using a quantum superposition. And lastly, we're also looking into investigation into other many-body quantum QCD bound state problems in the future. Thank you very much.
Thank you, Wenyang, for the very nice talk. And now we have some time for questions. Yeah, Felix.
Hi, yeah, thanks for the nice, interesting talk.
Thank you.
Maybe two quick questions. One, like on the first day, Bert de Jong mentioned that there can be these kind of barren plateaus in VQE and so on, that you somehow cannot optimize and things. Is that something you have to worry about, or does it not appear here?
It does not appear here, actually, yes.
Is there a reason to understand why it doesn't appear, or why it's not a problem?
Maybe it's shown here in some sense. This seems to be a plateau that it's hard to go across in the hardware efficient ansatz. I think because the hardware efficient ansatz doesn't have any restriction on the Hilbert space you can probe into. So sometimes it's getting into the local minimum, not a global minimum that you want. So it's very hard to get out of it. So right now, really VQE or SSVQE really depends on your the optimizer. The optimizer is the key to solve this kind of hybrid approach at this present stage.
I see. Okay. I see. And then maybe another quick question. So you mentioned that you evolve. There's a very naive question. Like you said, you evolve your PDFs with DGLAB, right? Like what?
Yes.
Like what scale? Like what determines the scale where you start?
Right, that's a great question. So so in the original Hamiltonian, we have here, and then we look at this particular basis. So the particular basis already give us a range of the potential energy scale of the model that we look at, and that is a very small energy scale. And for the VQEs, we treat that as an parameter, and then we evolve we do our decay version using the Qubit package, and then compare our valence quark distribution with the E615 data, and in order to then look at the smallest chi-square error in order to determine the initial scale.
Oh, I see. So, so sorry, E615. That was a Julian experiment. I don't remember. What was that?
I think it's a dijet experiment. Yes.
I see. I see. So, but then, so I mean, you write initial scale Q naught of 0.5 GeV, right?
Right. That is actually the parameter that has a bound according to the basis function, but that particular value, which is 0.56, it's not determined. And we basically we evolve with this as an parameter, and using the Hoppe package to see which parameter will give us the best agreement with the experiment of the valence quark according to this data. And in order, then we can determine this initial scale.
I see. But so then, are you using DCLAP like below 1 GeV for the evolution?
Yes, so we did. Yes.
I see.
Yeah. Just a follow-up question. Is it possible to calculate the DCLAP equation using your formalism?
Yes, it's possible. Yes. Yeah, that's actually what we did. The distribution we get are entirely valence quark distribution, but then we can evolve the DCLAP using the DCLAP, and then we obtain the other distribution as well.
I mean, the DCLAP you used is calculated perturbatively, and Felix is trying to ask it maybe reliable below 1 GeV. So I'm just asking, like in your formalism, do you have any non-perturbative method to estimate the DCLAP? Or non-perturbative estimate of the evolution?
So for my result, so I compute the parton distribution function at this cutoff, which is maybe 0.5 GeV around, and then I evolve that using the I think it's the next to next leading order DCLAP equations to obtain this distribution. Yes.
Okay.
So hopefully that answers your question.
Yeah, sort of. Yeah.
Okay.
Felix, do you have more questions?
Oh, that was the two questions. So I guess it's sort of like determined phenomenologically, right? So you basically find that it works, right? And then yeah, I see. Okay, great. Thank you.
Yeah.
Yeah, I have a question about the SSVQE. Like
yeah, sure.
You said the width has to be strictly descending or exceeding.
Yes, yes.
But I assume like if you choose 1.98, it won't work, right? So you need some like separation between the neighboring weights.
Yes. I actually tried different weight factor. So if you pick 1 and 0.9 and 0.8, 0.7, that would totally be fine.
Oh,
but
really? Okay. I see.
But I think if you pick 0.99 and 0.98, that might be difficult.
I see. That has to be related to the energy gap between the ground and the first excited state, right?
Yeah.
So how big is that gap in your case here?
That's quite big actually.
I see.
Let's see. So yeah. So you can see it's noticeable, right? So
yeah, right. That's something about 0.2, right? The gap of 0.3. The neighboring gap, right? You have 4 lines if I calculate the neighboring gap.
Yeah, but this is MEV square, so yeah.
Oh, it's MEV square. Okay.
Similar to that, yes.
Okay. Yeah. Okay. Thanks. And also, like for the ansatz, like are you sure these ansatz will lead to the true ground state, or is there any?
That's another very good question. Let's see. So the unitary couple cluster ansatz. This ansatz is very popular in chemistry. Also, it has many variations. Basically, it can evolve your state to a restricted Hilbert space. That's the guarantee to know that it's that includes your final solution. So this is very efficient. But and then you have this hardware efficient ansatz, which is not efficient physically, but it's efficient hardware by the hardware, because it's very, very short, and it utilizes the hardware connectivity and so forth. And in comparison, the unit capacitor will be much longer, but with fewer parameters. So there are pros and cons to each ansatz. Yes.
Okay.
So there's been a paradigm shift from the UCC ansatz to hardware efficient in chemistry nowadays.
Okay. I see. I see. Like you write down like the hardware efficient ansatz is proven to work for general problems. I see.
Yes. 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 Many other problems as well.
I see. Thank you. Felix, you have another question?
Sorry, yeah, so can I just ask one more quick follow-up question? Sure. Thanks. So you mentioned, so another question about the scale, like, is there a way you could like compute this at a higher scale? Like, you know, could you like somehow change something in the formalism to evaluate the PDF basically at a higher scale?
You mean without doing the evolution?
Right. Could you just, like, because like, could you get away like without the evolution? Can you just like, I don't know, calculate it at, you know, 4 GeV or whatever you showed in that plot, right? Would that be at all possible, or is that?
So to my knowledge, I think it's not straightforward to do. At least you have to do some modification to the Hamiltonian or to the original problem. Yes, but in general, our Hamiltonian it generally works below or around 1 GeV. So that's why you need the evolution to boost it to compute the experimental data.
Right. Yeah, I guess I was just wondering, right, if you, but one could like worry, right, if the DGLAB sort of works below 1 GeV, right? And so if you had sort of a way, right, yes. right, like it, so I was just curious if there's a way sort of to directly evaluate it, you know, at least above 1 GeV, right? Then one wouldn't worry about it anymore, right? I mean, maybe DGLAB is fine on there, right? But it's sort of, I would sort of worry if that's, you know, an uncertainty, right? And so if you could,
very good point. Yes.
But if you could directly evaluate it 1 GeV, right, that would of course completely solve that issue, right?
Right.
That's what I was just curious about. Okay.
Thank you.
Thanks.
Yeah, Felix. I mean, I want to initiate some discussions. Like, the renormalization scale mu in DGLAB. Is there some real physical meaning associated with the scale mu, or is just an artifact of perturbative calculations?
Yeah, I think it's just, I mean, at least, yeah, it's like an artifact, right? As long as you don't, I mean, you have to choose it in some way. In the perturbative calculation, you have to choose it so you avoid large logarithmic corrections, right? But of course, whether that's like it, I mean, but in principle, the evolution should be, it's like perturbative evolution, right? So you would normally want it not to start at least much below 1, right? And so I think like that's been like work also, you know, independent of this, I think, where people like try to, you know, start evolving from like 300 MeV on, right? And it's not, right, it's not necessarily wrong, right? I think it's completely independent of this, right? As well as some like older ideas, I think from the 90s or 80s or something, right? Where they somehow thought they can somehow do something at 300, right? And then they evolve it from there. And it wasn't, it kind of worked, right? You can, for example, right, when you do your PDF fit, right, you can like parameterize it at very low scales, right? And it's, I mean, I think there can be, you know, with a, you know, high precision, there can of course be some problems, right? But I think there were like some motivations like from spin physics to do it at very low scales, right? And then maybe related to some of these experiments here also. And then I think there are a couple of papers written where they really evolved down to very low scales. I guess like normally, right? If you want to be on the safe side, right, then, you know, you want to choose it like sufficiently large. But I mean, people have done that in the past, right, to evolve down to low scales.
Okay.
Yeah. At least that's from what I remember.
Yeah. Meijian, do you want to unmute yourself and ask a question?
I think you can hear me from here. So my question is actually related to the previous question that's about the cost function using the SS VQE. So you have the freedom of choosing the coefficient on the cost function. And you said that like different combinations of the coefficient, they would both work, like 0.9 and 0.8. versus 0.5 and 0.25. So I wonder how this will have an influence on the convergence of the result you get. So if you choose the coefficients wisely, will it lead to like a less requirement of less iterations to get the spectrum and the state?
I mean, it's really hard to quantify because that also depends on initial parameter. Right. For certain initial parameters in the unitary ansatz, you know, some weight factor will converge faster than the others. But if you change the initial parameter, the same observation doesn't hold anymore. So I would say it doesn't really matter for the initial for the weight coefficient. What really matters in the convergence is your optimizers. So for simulation on the classic computers, so quantum simulations, maybe a BFGS copilar works very well. But if you want to use real quantum backend, you have to look at some statistic optimizer that can will have some fidelity related to your ansatz. So that proven to work much better. So I think convergence is more related to the optimizers and the cost function design.
Okay. Okay. Thank you.
Okay.
Yeah. Any more questions? If no more, then let's thank Wenyang again.
Yeah, thank you.
Thank you. Yeah, I think we can stop recording